Hello everyone, I am Niyaz Ahmed from Yongnam University, starting my presentation on robust tension control of modern winder-unwinder Creel system using Kalman filter. This is the content of my presentation where I am going to focus mainly on system dynamics, control design, and experiment with result and analysis. In this industrial era, textile sector are like gold mine, especially for the developing countries like Vietnam, Bangladesh, and Pakistan. According to leadership and democracy research, only textile industry has added 228.4 billion US dollar in Bangladesh's economy from 2017 to 2018. And with 2019's international trade map data, you can see the developing countries are exporting a huge amount of clothing and footwear to European Union and the rest of the world, while as large economy like China, Turkey, and India is also contributing a handsome amount. Now, this is an estimation of per capita spending on garment products for large economic countries like Australia, Canada, and Japan. Although COVID-19 can affect this estimation, but overall we can say the textile industry has enormous potential in near future. So we should focus on improving the product quality to keep up with the market demand. Now let's see the basic principle of looming. As you can see, the loom is made up with two sets of wrap. First set has two rows stretched lengthwise and second set goes back and forth for between the wraps. Each individual wrap is threaded through an eye and a needle passes halfway to pass the wrap faster. Now, as we have learned the principle, we know that the better we can maintain a constant tension on the wrap is the better our product quality will be. But let's now discuss on the problem which we can face while working with the looming system. First of all, if we continue with a fixed yarn velocity, the rotational velocity of the unwinder will increase after a certain time as the diameter is changing continuously. In the second picture, you can see the effect of this phenomena. The yarn tension will be less and the product quality will decrease. But in order to maintain the velocity, if we increase the velocity of the rewinder intentionally, then it may cause churn of the yarn. Traditionally, to overcome this problem, mechanical controllers like brake or rotational weight are used. But what if we want to control the tension very precisely? As we know, the precise tension will produce better quality product. So our goal in this project was to design a precise tension controller with a velocity controller for a winding unwinding creel system, and also design a noise processor to reduce the noise of the load sensor. And also we would like to add robustness so that it can withstand different input. About the system introduction, this is our system with an unwinder and a rewinder motor and with some bearings. A description of the motor and load sensor is mentioned here, and this is the part which can control tension mechanically, but as we are going to control the tension only with the motors, we are going to omit this part. And for the dynamics, here we have shown the dynamics of the yarn system. As we know, the yarn tension will depend on the acting force Ft, then the direction of the force theta, then the yarn thickness theta wave, and also the angular displacement of the roll theta m. As in our system theta is 0, and the yarn thickness and angular displacement can affect the system very slowly, so we can consider these values as almost constant. So we have came up with this nominal model. For the motor dynamics, we are not going to control the electrical parts, as it is going to controlled with the motor driver. We are going to focus only on the mechanical part, and here you can see the uh, transfer function of the motor for velocity and position. About the control design, we have to design a controller which can control the tension of the yarn as well as the velocity of the motor. So we should go for a cascade controller, which is the outer loop, in which the outer loop will perform a tension control and inner loop will perform a velocity control. And also we have to use a Kalman filter so that we can reduce the noise of the sensor. And these are the details of controller transfer function, where we have calculated feed forward controller through pole zero cancellation method, and also we have added robustness through disturbance observer, which includes inverse plant and a Q filter. And here you can see the block diagram for our tension control system. For the velocity control design, we have used a PI feedback controller along with a feed forward. Also, we have used a disturbance observer, which will give us both performance and robustness. And for the experiment part, here you can see the connection diagram of our system, in which we have used a console board as our microcontroller, and we have used MATLAB Simulink to program that console board. First, we did our experiment to identify the motor parameters, and here you can see the details of each individual motors. For testing the velocity control performance, we have checked the performance of each individual motor, which shows a very good performance without connecting the yarn. But as we have connected the yarn between the motors, we can see some disturbance which mainly occurred due to uncontrolled yarn tension. Next, we have found the elasticity of the yarn by turning the creel in various positions, and this is the elasticity value. Now we will talk about designing the Kalman filter, as the control system is cascade control of tension and velocity. So it will be more logical if we design a Kalman filter taking a tension velocity nominal model. But the problem with this is we will get a derivative of tension as our output of the Kalman filter, which will give a noisy signal if if we integrate that Kalman and that output, it will become more noisier. So we have to design another Kalman filter model which will be calculated taking the tension position nominal plant, and here is the performance of that noise processing Kalman filter, where you can see similar shape with the raw data, and also the noise is reduced a lot. Considering this signal processor, we can design our cascade controller in two ways. As we are getting a position output here from our control tension control loop, we will consider that position as the correction input added with a integrated reference velocity, and perform a position control on both motors. With this control design, tension control performance was quite satisfying, but velocity error was not quite satisfying. So as our main goal was to maintain the tension and velocity, so we have came up with the tension velocity control system. Here we will differentiate the correction position output from the tension control loop along with a low pass filter, and use that velocity added up with the reference velocity, and we will perform a velocity control on each motor. And for the feed forward, we have used only the reference velocity, as the total input can be very noisy. And here you can see the performance of the controller. We have used different tension input in order to check the robustness and the performance, and both the tension and velocity performance was adequate. But for the industrial use, we need to keep the rewinder motor velocity constant, and to maintain the fixed tension we can adjust the velocity of the unwinder motor. So in this experiment we have added tension control loop with the unwinder motor. But if we see the performance, we can see a lot of disturbance, as the the load sensor is too far from the motor, and a lot of vibration are generated in betweens. So by analyzing the error with the Fourier transform, we have found that 5.3 Hz a large vibration occurs. So to omit this vibration from our system, we have used a peak filter, and in this plot you can see a better performance performed by the peak filter. Here is the real-time performance of the experiment. In summary, we have successfully designed a tension velocity cascade controller with different feedback and feed-forward controller, and we also have checked the Kalman filter performance. Also, different tension input was tested. In future, we would like to analyze the robustness, and also design different type of controller like ILC or high gain controller. Also, we would like to test the performance with the different type of yarn. Thank you, everyone.